All right. Good afternoon, everyone. Sorry for the delay. We had some technical glitches, Wi-Fi as usual. So, um it's happy to see you all after lunch. I thought, thankfully, we have not all had like a very, huge lunch. So we are all back here, and hopefully, I don't put you all to sleep. Leaving that aside, so this is what we're talking about is gossip protocols. The talk is gossip protocols for eventual consistency. Just a little bit about me. I'm Shriram. I work at Microsoft. I work on distributed system at Microsoft in Microsoft 365. We built an orchestrator service that deals with large amount of events that happens inside of Exchange, and that's order of some X trillions of requests per day. And beyond that, I've worked at Microsoft. I've been working for around 4.5 years. I've worked across the stack. I've worked on user interfaces to Outlook, and now doing distributed systems. When I'm free, I usually tinker with some systems programming. I do some Rust. I write some toy databases, and I like to build on things on the web. I occasionally have a blog that I write on. It's blog.shrirambalaji.com. And if you ever want to follow me, I am at Shriram Balaji on Twitter, GitHub, LinkedIn, everywhere. Right. All right. That's enough about me. So the agenda for today is how the first thing that you look at is what is gossip and how gossip spreads. We'll understand eventual consistency. We'll look at why gossip exists. We'll implement a node. We'll look at some tools called Maelstrom and deal with how we process those requests. We'll look at push pull and push pull protocols. We'll look at a Maelstrom runtime. All of these things might not be immediately something that you can understand in from the agenda, but hopefully by the end of the talk you understand everything in the agenda, right? And we also will also look at where gossip protocols are used today and where they might not work, right? Let's start with the story. So once upon a time, there spread a rumor, right? And there's this guy, Mr. Red, who here has 3 friends, right? And he spreads that rumor to 3 other friends, and they have 3 other friends, and they spread that to their 3 friends. So at this point, all of these people know what that rumor is, right? So as you might see from this pattern, the gossip actually spreads very similar to an epidemic, right? And we'll sort of live in the age of misinformation, where even a tiny bit of news can become sensational, can spread like wildfire without even being fact checked. We witnessed this as recent as 10 days ago. So it's all fresh in our minds in terms of how a small bit of news can travel far and wide, right? But if we can take that property that is a systemic thing among humans and put that into perspective for distributed systems, we get some interesting things that can be solved from applying this to distributed systems, right? And gossip algorithms are that exact manifestation of the same idea that humans gossip, right? The gossip algorithms are called epidemic algorithms also because of the nature that it spreads like that. So we understand now, hopefully, what gossip here means, right? That's the first part of the talk from the title. The other thing that the title mentions is eventual consistency, right? Eventual consistency, if you've read some literature about distributed systems, it's something that you have most likely come up about. So it's a weak consistency model that guarantees that all the nodes in the distributed system will converge to some state at some point in time. And Martin Kleppman, who's a renowned author, you've probably read his books. If you're interested in the distributed data system stack, you've probably read the DDIA book, right? Designing Data Intensive Applications book, which Martin authored. And he says that if no new updates occur, all the replicas will converge eventually, is the baseline understanding of eventual consistency. Like as with everything in life, XKCD already has a comic about it, and this is a comic where he's trying to evade work because he's being asked to test a database for eventual consistency. And what he jokes is that in a universe, in the cosmic sense, everything will be eventually consistent. We are all going to end up in a universe that destroys at some point of time. You'll all end up in a hot bath. So he's just getting a head start on that by actually never doing any work, right, at maximum entropy. Right, so we still can't wait for that amount of time. We barely have another 30 minutes to actually wrap our heads around gossip. So let's just get to that. So why gossip? For humans, gossip is emotionally rewarding. It's used as a tool to socialize. When you are envious about someone, if you don't like someone, you spread hatred. If you want to maintain social order, this is sometimes fun, right? But again, this isn't a psychology talk. Let's just talk about the protocol side of things, right? So what gossip protocols here enable is efficient dissemination. Dissemination is a fancier word of saying spreading, right? So it's just a fancier way to say spreading information among nodes in a distributed system. And the main goal is to have as much less minimal network bandwidth as possible while still being resilient to node failures, right? Cool. And there are a couple of tenets of why gossip algorithms work well and are used today widely. So they are scalable inherently, right? So they use O of n, log n rounds and constant size messages to reach all the peers in the network. So it can scale smoothly even to thousands of nodes. Just in the next slide, I'll talk about why they are log n. And they are fairly simple, right? As I was explaining, the core algorithm itself, in its nature, is very simple. Each node picks a random peer every round. It exchanges some bit of information, and then it waits for the next round, and then keeps repeating until there is natural convergence inside the entire system, right? And they're resilient because fundamentally what every node is doing is just waking up and then sending messages and then waiting for the next round, right? And by definition, what that would allows is that since the messages are going to get repeated throughout the network, it naturally tolerates if there are issues in network partitions, if there is a node failure, if there's a message loss. There is at an eventually consistent point, every node is going to get that information anyway, right? So this is the fault tolerance mechanism. And another thing is that you might think this always requires TCP. It is always good to have TCP, but this will also work on UDP protocols also because it is fundamentally resilient to all of these network losses that might occur. And it is also decentralized. You don't have a quorum or a centralized leader. You don't need to have a consensus mechanism because it's a weak consistency model. Unlike other strong consistency requirements, it's not the same set of rules that are required, and there's no single point of failure that happens in the system also. Right. So I said what is that gossip algorithms are O of log n. So let's take in each round R, if there are the number of nodes is multiplied by a fan out factor of f. So until we reach, let's say the total number of nodes are denoted by n, right? So in every round, it sort of goes from 1 to f square till it reaches f power n. F power r to reach and when it reaches f power r, that means that all the nodes in the system have converged. That means the information at the last round, which is f power r, that means that all the information has passed to all the nodes in the system, right? That's what that f power r means, right? So now just putting it into perspective, if we say we take a fan out factor of 2. When I say fan out factor of 2, that means that every node basically picks 2 random nodes in the network and then sends a message to 2 of them, right? And every other node does the same thing. So that's what a fan out factor here is. And in total, if you have 16 nodes in the system, so you will basically get that in 4 rounds, right? By the time we reach 4 rounds, we are already there. And if you solve, so if you say what I was mentioning is f per r is n, right? If you solve for r, you would get r is log of n. So per round we have log of n is the asymptotic format, and we take it in the asymptotic format, it comes down to O of log n. Hope that's not too much, right? All right. So we understand what gossip is. We sort of get the theory, right? Let's actually start diving into the implementation itself, right? So the first thing that you would see in a gossip node is it has some state, right? Every node in a distributed system needs to have some state, right? And in our case, we'll keep it very simple. Our state has only 2 things, right? So the scene here is a unique set of message IDs from that the node is seeing, and neighbors is just a list of all the neighbors that the node has in the system, right? So when I say message ID, so message ID here, you can think of it as just as a number that just monotonically increases throughout the system. It could be a GUID in some sense, or you could have some way of identifying it as a unique identifier. But for our purposes, let's just say that this is just an increasing counter of some sort, right? So as I already mentioned, that it represents the unique set of messages ID. And so, but there is one small nuance here. The implementation here is going to be in Rust, right? And I don't assume that a lot of you know Rust, but even if you do, that's great. Even if you don't, that's okay. The point of this talk is that you take away with a solid understanding of what gossip is and not be bogged down by the syntax here itself, because fundamentally the idea is that the more time you look at spending, the more time you spend looking at the syntax, you might be confused on what is happening. That is not the whole point of the talk. You can implement this in any language of choice. You can do it in Go, and you can do it in any other language of your own choice. But the point is that you understand the system and then walk away with that, right? But since the implementation itself is in Rust, I'll have to go into some details here and there. So please bear with me there. So we know what a mutex is here, right? So the node state is actually wrapped in something called as an arc mutex. So the mutex is just a lock around a node state, right? Why do we need a lock? Is basically you have multiple threads that are going to access this particular node state. So we need to be able to lock so that we can spin up a one thread or an async task can actually read or write at any point in time, right? So I think that is fairly understood of what a mutex is in multiple languages. So I don't think that requires any further explanation. But arc is an important primitive that you might run into whenever you write any async Rust or anything that requires concurrency in Rust. You would run into this something called arc, right? So, but before you understand arc stands for atomic reference count. So, but before you understand what an arc is, you need to understand what a reference count is, right? Okay, so this is a slight detour into what reference counting is. But let's say there is a string that is allocated in the heap, right? We have a string, and there is one reference to that A, right? And there is one reference to it at some point in time. Now we need to have another reference B for the same string. In most languages, you could just have multiple references to the same thing in the heap. That is possible. But in Rust, when you have one particular thing, there is only one owner for anything that has an allocation. So when you take this reference and B starts pointing to it, it is called as a move. So when something moves, right, that means that B exclusively now starts having reference to this. This solves a lot of different memory safety level problems. I don't want to get into that particularly, but you just need to understand that there is an exclusive reference to something that is present on the heap, right? Okay, great. Now we have an exclusive reference, but I don't want an exclusive reference. I need multiple threads being accessed or multiple things. I need both A and B accessing the same thing. I don't want a move, right? So what you do then is you wrap this in something called as a reference count, which is called as an RC. So when you wrap something in an RC, so basically I take the string and then wrap this in an RC. What happens is that now you can have as many references, and then what the compiler will do is will count every reference. So A has one reference, B has another reference. So we have two references. Take that same problem, and now this works only on a single thread. What happens if this problem scales in multiple threads? I need to access the same string across different threads. So this string is no longer thread safe, right? So that number of the counts that we are doing need to be atomic. That is where the atomic reference count comes in, where you across multiple threads you have some allocation that is in the string. Some string allocation or whatever it is on the heap, you have atomic references to that. You know that the number of references that are there for that particular string, you can basically the compiler knows how many are there across threads, right? So that's the compiler's way of keeping track of how many references are there for this particular thing. Again, this is much easier in a lot of different languages, but the way Rust solves this is for very different reasons than what other languages might do it, right? So I think there's yeah. No, it's in terms of this, let's say for our implementation, we are spawning multiple nodes that we are going to simulate. It might not happen so that I'll get to why we are doing it in a minute, because for our implementation we need to have multiple nodes because we are going to simulate this as a distributed system in our own setup. Because again, we can. I guess I don't know who said it. It was when we had this in our conversation. I think it was Krishna or it was Rahul, where they were saying that we can write a system, but writing it perfectly is the bigger problem. So what I'm going to write here is something that is is a simulation, but it's not entirely what it is. So I need to set up some context so that when the simulation actually comes, you have a fair bit of understanding. So I think the concurrency model is more or less clear, right? So we have a mutex that is taking a lock on that particular data, and we have an atomic reference count, right? So this is in the sense of you have multiple threads, right? You have physical threads that you're spinning up in the operating system, and then each of them are having a reference to this particular data. But when you're talking about an async runtime, right? You're not spinning up threads, you're spinning up tasks, right? Which is you can draw some parallels to that to coroutines, but they are starkly different in terms of how they operate, right? Like coroutines and this are an exact opposite of how they operate. I'll get to that in a bit. But one thing that you might have sort of understood just from the gist of this is async Rust in and of itself is a much harder paradigm, unlike other languages where async primitives are much easier to do. So async Rust is hard because it has something called stackless routines. So stackless routine here being every task that I spin up does not have its own stack. Every task has it basically returns a future that turns into a state machine, right? I'm just trying to put into perspective that writing async Rust might not be immediately evident, and so coming back to the same point of not being bogged down by the syntax, right? This is sort of widely acknowledged across a lot of experienced Rust engineers as well, that async Rust in and of itself is a different language altogether. Keeping that aside, the another problem that you're going to run is simulating a distributed system is a very difficult task. How are you going to spawn on each node? We have to spawn it on a thread or a process. You have to wire up the I/O. You have to inject failures. You need to deal with partitions. You have to correlate all the logs from all of these different nodes and put it into the same place. So this is a very, very difficult thing to do, right? But we also need to learn how to do this, right? We need to have our own toy implementations, as I think Arpit was talking about earlier. Is if you have a scenario where today you're able to you have enough leverage to actually build enough knowledge to anything that you want, any theory that you look at, right? You are able to build it, take that and put it into practice with the help of LLMs or whatever that exists today, right? And in that scenario, what we want to do is learn by doing, right? So, and that's the whole idea, is that we are going to try to learn a gossip protocol just by doing something, right? And for simulating, there exists tools in the ecosystem, such as Maelstrom, right? So Maelstrom is Maelstrom and Jepsen. I'll get to what Jepsen is. So Maelstrom is what is it is a workbench. It is a workbench for learning distributed systems. You can write your own distributed systems, and then it uses fundamentally it is an abstraction on top of Jepsen, which is another library. So you can test your own toy implementations of distributed systems. So what is Jepsen is? Jepsen is an industry standard for validating databases, distributed systems that are built by it's built by Kyle Kingsbury. He's also known as Afer. And a fun fact is that he had a series of blog posts when Jepsen itself came out 10 years ago. He had a series of blog posts called "Call Me Maybe," which is based on the song "Call Me Maybe" Carly Rae Jepsen, because it's a nod to distributed systems in general. What does a node do? Call me maybe, right? So that is basically what the series of blog posts were, and you can still find them online. It is a series of reports on MongoDB, Elasticsearch, and all of different sets of distributed systems, right? Cool. So internally what Jepsen is just a closure library. It is a testing library that what it has is it's a control program. So what that control program is going to do is you can give it access to any binary or something like that, and it will basically SSH into a bunch of target machines and then deploy your system and then spawns the client process for all of those systems. So this is what Jepsen is doing internally, right? We don't particularly want to go into depth of what Jepsen is doing or how it is doing it, but we just need to understand that it is able to do the simulation that we were talking about earlier, right? And there is a nemesis that keeps running in the background, which keeps injecting fault in the system. When I say injecting faults into the system, I mean things like a loss of network partition, or a message loss. All of these different scenarios that you would run into when dealing with actual distributed systems, you can simulate them with Jepsen, right? And another important relevance with Hasgeek itself is 10 years back, I saw this talk for someone he was working on Apache Solar. Shalin Mangar's talk on running Jepsen tests for Apache Solar. So this is a technology that has been that is existing. This tooling has been there for a decade or so. So I think it's robust enough that we can build on top of it and learn how to do it, right? So as I was saying, Maelstrom is an abstraction on top of Jepsen. It is built by the same Jepsen team, and it is a simple JSON protocol. It has a very simple JSON based protocol and has a CLI. Right? What the CLI allows you to do is you can specify the number of nodes that you want to spawn. You have a target binary executable, right? And you have workloads, right? What are workloads? A workload is specifying what the operations that need to happen in a distributed system, right? For example, in a broadcast workload, the nodes will have to submit two things, right? Either they can broadcast the information that they have, or they will read the information from the system, right? Those are the two things that are going to happen in a broadcast workload, right? And the API itself is simple. It has read, broadcast, and a topology. We won't particularly talk about the topology workload part of it, right? But what the understanding here is that from Maelstrom has a standard of how these nodes basically talk to each other, right? They have a protocol of how these nodes have to talk to each other, and if your system implements that protocol, you're able to simulate that and then understand how your system is performing under that simulation, right? So that's what Maelstrom offers. So in this test for a broadcast workload, what is going to happen is that it's going to intermix reads and broadcast operations, and then after a point of time, it's going to do a final read to check if the things have converged, right? In the duration, it will check if there are messages are lost, or if the state is valid after all of these tests have run, right? And this is what a request itself looks like. So that you have a source, you have a destination, and you have a body. So where N1 and N0 are the source and destination, and the body looks like has a type and message ID and message and things like that. When a broadcast does happen, you respond back with a broadcast OK, right? And the in reply to mentions which node you are actually replying to, right? Same thing for read also. I think that is straightforward, right? So now we'll get into actual code. We'll start getting into the actual implementation part of it, right? So every node in your system needs to have something called as a process method, right? So what that process method is going to do is it is going to handle the incoming messages that are Maelstrom, that are from the that are from the Maelstrom protocol, messages that are that work with the Maelstrom protocol, basically, right? And here, when you match on the types of messages, first I told you that there is a read operation or a read request, right? In the read request, what happens is you take a snapshot of all the messages that are there in the system, and then you send it back to as a reply to whoever was requesting it, right? And there is some syntax in terms of Rust itself. Is you see this impl block, right? So impl is denotes an implementation of the struct that we saw earlier, right? I think it's whatever behavior or whatever behavior you need to code for that particular struct, you put that inside an impl block, right? And here what the method that we are having is the snapshot method that we saw from the last slide, right? So we are locking the particular state. We are iterating through a list of all the scene messages, which is all the message IDs. And then we are collecting that and giving it as a vector. We can think of it as an array list of 64-bit integers. So here it is a 64-bit integer because, again, it is the unique message ID that I was talking about earlier, right? We also see the syntax called self. So you get something called as a immutable reference to the gossip node. It's not we are not mutating anything inside the gossip node itself, so it's not particularly, we are just getting it state and locking it and doing some things on the top of it, right? Okay, so there's another method called triad. What triad is here is doing is it's again locking the state. It's just checking if a new message has there is a new message that has come up into the system, and it adds it to the scene list for that particular node, right? I think that's pretty straightforward. Hopefully there are no questions there. And when it comes, where that triad method is going to be used is when we talk about a broadcast. So when we are processing a Maelstrom broadcast request, what we have is we'll take in, we'll try to add the new message that has come in, right? And then broadcast that same thing to every neighbor, right? So what the algorithm here is, it is iterating through every node's neighbor and then fanning out that and sending a message to all of them, right? So this is a typical broadcast, right? We haven't gotten to the point of where this turns into gossip. We are still doing an O of n where every node is basically telling that message to every other node, right? But what we want is randomized gossip, right? So the main change here is what we are doing is we are sort of doing a neighbors.shuffle. So the RNG here, you don't particularly have to think a lot about that. Is think of it as a thread local generator that is giving me a unique number to generate, change the order of the neighbor's vector for every time this broadcast request happens, right? So think of it as just to put it simply, just shuffling the order of the neighbors that you have, right? So that is the randomness part of it, and then you're taking only 3 of those subsets. So in our case, the fan out factor here in this code is 3. So what that means is you are sending that particular broadcast only to 3 nodes, right? So what we sort of understood here is the gossip protocol by itself is probabilistic, right? Where each node forwards an update to a small random subset of peers, right? And what we also saw is also the other name is what is called as rumor-mongering, right? So, and the simplest rumor-mongering algorithm we have is where every node keeps a set of message IDs. When on the first receipt of that particular new message, it selects a random number of peers. In our case, it was 3, and then pushes the rumor to them. Peers do the exact same thing until the rumor floods to the entire cluster, right? So, but what we are doing is also pushing, right? We are also basically pushing the same information to all the nodes in the system. That is why this is called as a push-paste protocol, right? There are different types of protocols in gossip itself. There's push, pull, and push-pull. Push, we already know what it is. Every informed node actively sends updates to every other node, right? It's fast, and but it wastes a bit of bandwidth, but it ensures that there is fast convergence, right? But the pull is the opposite of this, right? So where every uninformed node basically pulls for data, right? You can see that there could be a problem here that even after a given point of time, you might be pulling information from your random neighbors, but they might not have the information. So there is a very good chance that even after O of log n rounds, you might still the information that you're looking for in your node is not there at all. Right, so that is why it has a very slow. It has a slow start, but it catches up very quickly, right? push pull is basically a combination of both, where nodes actually push new updates and then they pull digest of whatever is missing, right? So this leads to a scenario where you initially spread a lot and then late stage conversion. This is also very efficient, right? But one question that you might have thought about is, we've implemented a node. We know that we know what the core gossip algorithm is. We've talked enough about all of the randomization that happens and then the subset of peers that you send information to. But what is actually powering all of this, right? So how does a gossip node that we've implemented, how does it execute the RPC calls to handle all of these replies? And how does the gossip node parse the Maelstrom message? How does it actually know who its neighbors are, right? So for all of that orchestration, you need something called as a runtime, right? A runtime that understands the Maelstrom protocol, a runtime that can do all of this work for you, right? So we'll quickly go to the runtime implementation. I'll not spend a lot of time on the implementation itself because it might be slightly complex, but I'll try to walk you through that just quickly. All right. Let's look at the runtime quickly. So the runtime here, hopefully this is visible. If not, I can zoom in a little bit. Little more. Work? Does that work? Perfect. So the runtime here has a wrapper on its own inner state, and it has its own executor. So what the executor does is basically it has the job of actually spinning up the asynchronous task that we're talking about, right? Again, in a system where these nodes are actually physically distributed, you don't need that, but you need it in a scenario where you're actually just spawning async tasks just to simulate the system, right? And there is some state that the runtime needs to have, specifically the message identifier that needs to be which I was talking about needs to be incremented every time, right? There's also a cluster. A cluster here is just a bunch of nodes. All the nodes in the system are represented as a cluster, and the current node is also mentioned is also part of the state. And you also need to keep track of all the replies. So basically, if a node sends a message, right, and we need to keep track of something has replied to it or not. So that's also in the state. And then all of the Maelstrom works mostly because it's a CLI that takes in standard in and standard out. So we need to have a channel for just the standard out, so that all the messages all the JSON that we saw from earlier needs to basically be pushed back into standard out, right? We see this is the message. So this is the node in itself, right? So this is what we see is a trait. Trait basically means behavior, right? You can think of it as an interface in other languages, right? Sync and send are marker traits. Will not get to that. This sync and send just means that this is thread safe across. This is thread safe, right? And then we have a process method. All right, so the actual core here is there's a run method that somewhere over here that we will get to. Yeah, so the run method is the main thing in the runtime itself. What the run method is doing is basically just looping through every line in the standard input and then processing that input, right? And when it processes that input, if it knows that it is a reply to a message, it does so accordingly. If it is the first message, it has an init message thing, or if it is just a regular message, it actually just calls the process method, right? So the process method that we saw from earlier, which is over here, right? So this is the process method. I think that's all I want to particularly cover in terms of what the runtime itself is doing. The executor, as I was saying, is just a Tokyo spawn. So when you say spawn, it spawns a new task for doing something, right? So that's all. That is all you need to understand about what the executor is doing. So we saw what the runtime can do, right? We know what are the orchestration that the runtime is doing. But one thing that we didn't actually do or look up is how do we actually handle network partitions, right? Our system is still not fault tolerant. Our system does not handle what happens if the process method I talked to you about does not particularly handle if a message is not acknowledged by some other neighbor or a peer. How do you handle that? We've never talked about that up until this point, right? So let me go back to a little bit of code again. But now instead of looking at the runtime, we look at the actual implementation that I showed you in slides in code, right? So we saw the same, the Maelstrom node is the node that is represented from the runtime. We have the process method here. The main distinction here is we have a new state variable called as anact. That should be somewhere over here. Yeah. So the node state we originally saw that had only seen a neighbors. We need to keep track of a message ID and the unique set of all the neighbors that have not actually acknowledged that particular message, right? This is important so that we can do a retry mechanism. Basically, I send you a message, you have not responded back. I need to retry that. I need to keep retrying that so that in the system, there is no message loss even at a given point of time. So that's what the unact does. And in terms of logic itself is not very different. What the retry method itself is going to do is the same thing. It's going to spawn a background task. It's going to spawn a background task that keeps checking every 1 second or something like that of a fixed interval, right? It gets a list of all the neighbors, that have not acknowledged a particular message, and then does the actual gossip algorithm. Here, I hope you remember that we had this shuffling thing that is going on with the neighbors. We are again looping through the list of all the neighbors and then sending a message to just the neighbors who have not acknowledged this message. This sort of scales because we have now retried, we've also added a retry mechanism, and we are now able to make sure that the system is also fault tolerant, right? The last bit of this is actually putting it to test. I don't want to open Spotify, sorry. Oops. All right. Okay, this is live, so let's see if it works. All right, so I don't know if this is visible. Let me zoom in a bit. Okay, so what we're doing is we're calling the Maelstrom CLI. It has a bunch of arguments. The W points to the workload that I was talking about. The bin is the executable that we had, which we built with Rust. The node count, we are spawning 10 nodes, and the time limit is 30 milliseconds, right? And you can also specify this partition. So the nemesis that I was talking about here is the partition means it spawns, it simulates a network partition, right? So when simulating a network partition, we'll see what happens. So it's going to spawn 10 nodes. It's going to take roughly 40 seconds to 50 seconds to spawn that. So what is happening here is you can see Jepson and working here. It is creating all of these nodes. It is spawning up all of these nodes and broadcasting, and you can see it is intermixing a broadcast and read. After it finishes, it might be easier to view, but what you need to understand from here is that the Maelstrom allows us to intermix all of these messages, and then when eventually all of these nodes have finished processing all of the messages, there is an analysis step that runs that makes sure that anything that is sent between all of these nodes, did they ever land or not, right? So it is interpreting that, and it is waiting for recovery. It has stopped all of those partitions. It has stopped spawning those networks, and then now it is tearing down the entire network and then giving you an analysis, right? So your analysis basically works if it says that everything looks good, and if you have implemented something in the system that does not fault tolerant. Say for example, if you remove the retry mechanism and if you give a partition, if you try to do a partition, what you would see here instead is that the analysis is invalid. It would say that you have stale messages in the system, you have basically missed messages that have to be needed to be sent across the system, right? And I don't want to particularly go through this entire analysis, but what you need to understand is this validity and how many messages we sent. We sent roughly 300 odd messages. The sent count itself is 127,564 messages between these 10 nodes, and per operation we sent 426 messages, right? This scales logarithmically. If you think about this, if you do the same thing in terms of just doing multi-node broadcast, this would not scale because you would have so many more nodes, and a lot more messages would be sent in that particular same time frame. That is mostly all I had. We saw a demo, we saw what Gossip is doing, so I think that mostly serves it. Any questions that you might have, we can take now. One particular thing I forgot is where does Gossip actually work? Like we spoke at length about what Gossip doing here, this and that. Where is it actually being used today, right? So you need a Gossip protocol is generally used to maintain a list of all the available nodes in a cluster, right? Cassandra DB, for example, uses Gossip for just maintaining group membership and then failure detection across nodes. Another important thing that some of you might have come up if you have used Hasgeek or Surf and tools like that is a Swim protocol, which is scalably, weekly, consistent infection style process group membership. It's a fancy way of saying maintaining group membership through Gossip. So what happens in Swim is every node failure, it is used, Swim is exclusively used for failure detection, again membership, right? So what happens is if there are nodes that fail in the system, it is reinforced by all the peers. So let's say one particular node fails. I don't particularly say that the node has failed immediately. I wait for all of my peers to confirm that that particular node has failed, right? And when I understand that the node has failed, I spread that as an alert to the entire system. Redis also use this. Redis or Valkey also uses the same. It does not use Swim, but it does use Gossip for the same liveness and membership sort of thing. And CockroachDB use the same thing. I already talked about HashiCorp Surf, right? So that's all. Where it does fizzle is when you need strong consistency. You have a transaction like system. If you swamp your bandwidth with so much message, right? The messages are supposed to be constant size and fixed. If you are sending a lot of messages through in the system, you can immediately start seeing that this fans out in a bad fashion, right? And Byzantine faults, like for example, S3 in 2008 had this issue where they were using Gossip, and one particular node in the system had some bit flip or something like that, and because of that bit flip, what happened is that state propagated throughout the system, because the Gossip eventually the spread so fast that they had to manually shut down some of it, and then actually reboot some of those nodes and then update the state. So this is also this is some areas where Gossip can fizzle. So I think that is all. I think I was over time by a bit, but yeah. Hopefully, I didn't take, since the last talk, hopefully it should be okay.
So how do the nodes discover each other in Gossip when you added 10 nodes, right, or whatever? But in a real-time system, you won't know how many nodes you have because you can runtime scale and scale up and scale down. Like for example, if it's a database like Cassandra, right? So how do they actually detect?
I haven't particularly looked at how Cassandra is actually doing it, but I'm assuming there is some sort of an orchestration layer that sits up on top that does the node level discovery. Because the node by itself, it's supposed to be in its that would be some sort of the orchestration layer would mention to each node what its neighbors are or what its peers are, right? Even in our case, the runtime is what is mentioning what the neighbors of the of a particular node is. The node by itself does not know about anything other than the information that it already knows. So all of that information has to be provided to the node.
Okay. And what about a record or something getting updated at two different places at two different times? But eventually it will take time to, when the two records got updated, all of the nodes were not in sync. So how do they then get synced when
so
a
the
record
updates keep getting pushed at some point in time? It is that is why there is no guarantee. If this does not work in a transactional system where you need to make sure that all of them have the same data, that does not work there. Where it does work is basically when eventual consistency is what you need, where at some point in time everybody would get the same update, but there will be stale reads. There will be issues where a node has earlier information or a node has newer information. That is bound to happen, and the nature of the system is that. So it is by design, it is going to be having that as a behavior. Yeah.
How is the value of f decided?
That's something that you play around with and then you decide. But depending on how much, like there is also some TCP overhead, right? How many nodes that you want to actually talk to at any given point of time. It's something that you decide based on when you implement it actually. Because the moment you start increasing the fan out factor, you are sort of going into from log n to n, right?
I don't understand the trade-off. If you increase f to like, what?
Now, how are you? If it is n, so if it is O of n, what is going to happen is you are going to make sure that every node of the system is updated every time, right? That does not practically scale when you are doing it for 1,000 nodes or 10,000 nodes. But when you say a random subset of 10 or 20, the amount of time it's going to take for convergence is still going to be higher. But you can make sure that all of those systems actually get the update. But the problem with when you're saying that one node is going to talk to 10,000 nodes, you're going to spin off 10,000 independent TCP connections, right? All right. Thank you so much. Thank you, Rootconf.